Okay, so in this video, we're going to talk about the position tolerances that we're adding to locate the 4 holes and the 2 threaded holes on our faceplate to fit here on that front face of our frame. Okay, now as we look here, you'll notice that we have clearance holes for which our 1/4-20 socket head cap screws are going to go through, and they are going to thread directly into this front portion of our frame. And those are threaded holes. Okay. Now, remembering back to GD&T, there was 2 different types of positional tolerances that we apply. And one was called fixed and one was called floating. Okay. So what I want to do is, this right here. I want to revisit some of those concepts. So we had fixed and floating. So I'm gonna show fixed here first. So fixed fastener situation is when we have a clearance hole in one part and it threads directly in the other. That's exactly what we have going on here. And to determine what the tolerance is, the tolerance is going to be the value that we put into our feature control frame. We say that that is going to be H minus F divided by 2. Now the H is going to be equal to the MMC of the hole. So the MMC size of the hole, and the F is going to be the MMC size of the fastener. Okay, size of the fastener. MMC size of the hole, that's an internal feature. Is that the smallest or the largest hole size? It's going to be the smallest hole size. MMC size for a fastener. What did you say? It's going to be the farthest outer diameter. How do we determine that on a fastener? If we're purchasing a fastener, the MMC size of the fastener is the what size? What do we call that? Do you remember? Starts with an N. The nominal size. So if it's a 1/4-20 socket head cap screw, okay, that means a 1/4 inch, it's its maximum material condition size. That's as big as the outside of the threads can get. Okay, so this is always going to be the nominal size. That one's kind of easy. Okay, now MMC size of the hole. So for our case here, our hole size is specified at 0.265, right? It is a 3-place decimal. It defaults to the tolerance in the title block. So that means that our MMC size hole, okay, is going to be 0.265 minus 5 thousandths, okay, because that's the tolerance that's on there. So my MMC size of my hole is going to be 0.260, okay, and that's the MMC of the hole, all right? The MMC, as we had just stated, for our fastener, diameter of 0.25 is going to be the MMC of the fastener. So 1/4-20 socket head cap screw 0.25. It's always going to be that nominal size. Okay. So now we're going to take these 2 values, we're going to plug them into our equation. So T is equal to H minus F divided by 2. I'm going to take 2.260 minus 0.25, and I'm going to divide by 2. All right. My tolerance is what? So this is 10 here, right? And this is going to be divided by 2. It's going to be a diameter of 5 thousandths. So the number that we put in here is going to be 5 thousandths, not 8. I just had it in there as like a holding place. I wanted to show you guys the calculation. And it's also going to let me know that you were listening when we did the lecture. Okay. So this is going to be 5 thousandths, a diameter of 5 thousandths, right? Not for any other reason than it's how this is fitting together and because it's a fixed fastener application. Okay. Do you guys remember that from GD&T? I know who had me. Better. Okay. All right. If it's been a little while, I'm sure if you had it with a previous instructor, you hit this somewhere along the way. Okay. Now, the other type, which we are not going to be applying, I just want to remind us of that, is there's another type. It's called floating fastener. Okay. Floating. And floating is T is equal to, so the tolerance that we're going to put in our title, in our feature control frame is just simply H minus F. There's not a divide by 2. And that's when we have a situation where we have a fastener going through 2 clearance holes that's probably going to be fastened on the back side with like washers and a nut. Okay. So it's not threading into an item. Okay, so same thing up here, MMC size of your hole, whatever it might be, and then minus the nominal size or the MMC size of the fastener. And then you just don't divide by 2. So it's a bigger tolerance. It's double. All right. Again, we're not going to be applying that one. So we're going to fix our number to be 5 thousandths here. Now, you're going to notice with positional tolerance. So you need positional tolerance, diameter of whatever the diameter of the tolerance zone. So now the diameter of the tolerance zone is a circular tolerance zone that is going to be located at the intersection of the basic dimensions, right? Basic dimensions. Basic dimensions are the dimensions that have boxes around them. What's special about basic dimensions? Do you guys remember? They do not have the title block tolerance, right? That applies to them. So these are not going to be plus or minus 5 thousandths up and down. But that doesn't mean there's not a tolerance on it. At the intersection of these locations, we have a diameter of 5 thousandths at the maximum material condition of that hole size that we get, right? Now, the MMC modifier means that we get a bonus tolerance. Each time we make this hole a little bit larger, remember the MMC size is the smallest size. I get 5 thousandths there. Every time I make it a little bit larger, I create more room for that fastener to go into. And now I can allow that to deviate around a little bit more. So we're going to create our little chart. Do you guys remember charts? The best. All right, everybody get out. I want 3 columns. Here we go. Size. Allowable. Positional tolerance. Everybody's doing it. And what is this last column? Do you guys remember? Virtual condition. That's right. Everybody's writing this down because you're going to be handing this in. Aren't you excited you get to do a chart again?
No, because I have a calculator that does this. Can you just send a screenshot of it in the Excel file? Yeah.
Nope.
I made something to do. He spent 8 weeks. I'm using my resources in my classes. Sell it my learning.
So good.
Sorry.
Remember, we start our chart with the MMC size. Okay, so the MMC size is going to be the smallest hole size here. We know that to be a diameter of 0.260. You're just handing in the chart for me. I'm not going to make you do the calculations because I didn't tell you I needed to hand those in. But when I saw everybody staring at me and not like getting excited to write this down, I needed to have you guys step it up. In 1,000ths increments, we're going to go up to the largest size. We don't have to do all of them, but let's do a couple here. 0.261, diameter 0.262. We would add 5 thousandths here, so we'll kind of skip a couple. We're going to do a diameter of 0.270, right? Now our top line, we know that the MMC modifier is present, okay? So since our MMC size is 0.260, we're going to line up our allowable tolerance at MMC. It's not the 8 thousandths. Remember, we calculated 5 thousandths, okay? And then virtual condition. We are applying this tolerance to a hole. Is that an internal or an external feature? It's an internal feature. Internal feature means we're taking material away, right? So an internal feature, INT, virtual INT. We're going to take the MMC size of that hole, and are we going to plus or minus the tolerance? Do you remember? Minus, okay? It's a minus. So for internal features, it's MMC minus the tolerance. For external features, it's MMC plus the tolerance. But we're on an internal feature. This is the hole. Okay. So now we're going to calculate the virtual condition. So we're going to take our size, MMC size, and we are going to subtract the tolerance. So this is going to be a diameter of 0.255. Now, when the MMC modifier is present, we have one common virtual condition that goes all the way down that column, right? So we can say all of our sizes are going to have a worst case scenario of 0.255. So now what that helps us to do then is every time we make, and this is that saying that I have, every time we make this hole a little bit larger, we create a little bit more room for that fastener to go through. So we can allow this to move a little bit more because our worst case scenario is always going to be our virtual condition. Okay. So in order to do that, if I take 0.261, I made that hole a little bit bigger. Do you see how a diameter of 6 thousandths, and when I subtract it, I still get my worst case scenario. And then here I make that hole a little bit larger. I can actually deviate a little bit more and I still get the 0.255, right? So now when I have 5 thousandths here, and if I have a total range on my hole size of 10 thousandths, that means that from the MMC size there, I'm going to get a bonus tolerance of 10. So I'm going to say a diameter of 15 thousandths down here at the bottom. And if I subtract 15 thousandths from 0.270, still get that. I get a bonus each time. Now, this is because the MMC modifier was there, right? I don't get a bonus if I don't have an MMC modifier, right? If this is not there, there's no MMC modifier, what happens? You guys remember what happens to this column if I don't have an MMC modifier? It's going to stay the same. Exactly. So it's going to be 5 here, 5 here, 5 here. I still get a tolerance, but I don't get a bonus and I don't get a common virtual condition, right? Because this would change each time, but this would remain the same. So it's important when we have parts that are always going to be intentionally clearance, like we see here, a clearance fit with our fastener. Those are always going to be MMC modifiers. When we have something that we want to locate or we want to press fit on, those are going to be the, regardless of feature size, no modifier in back of it. Okay. So any questions about the tolerance box here? Also, don't forget the diameter symbol. Why is it important that we have a diameter symbol? It's a circular feature. The tolerance zone is also going to be circular. Excellent. Datums. All right, now the datums. The datums are important because the datums identify what we are going to be creating this feature in relationship to. When we create our datums, the first primary datum will always be the main mating surface, the primary mating surface. So as we look at this in its assembly form, okay, and if I look at this here, okay, this is going to sit. So this surface right here is what's mating with our surface on the actual arm. So that means that that side, the flat side, is going to be a datum. I want my hole diameter, okay, its tolerance zone to be perpendicular, and that's what you see here. That's just the center line. I want that to be perpendicular to this datum. It sets the orientation first in this case. So I qualify that. I say, oh, I want that to be nice and flat. And remember, flatness, we just need to be a refinement on the tolerance on the width of this part. So in this case, the tolerance on the width of the part defaults to the title block plus or minus 5 thousandths. That means I have a total of 10 thousandths. But I want this to be nice and flat. So I'm going to take something, I'm going to specify something in my feature control frame for flatness to be a refinement or something less than what this size allows, right? Because size tolerances control form within their pluses and minuses. It's when we want to refine on them, do we add a form tolerance like this? So I want to go over that. I want to do a nice little cleanup cut on that. So 5 thousandths. And once that's got its cleanup cut, that's now our primary datum. Okay. And A is the first datum that we have on our drawing. So it becomes A. Remember, the order of precedence here is not based on alphabetical order. It's based on left to right order, but your first datum is going to be the first letter of the alphabet. You don't start in the middle of the alphabet on a drawing. Okay. Secondary and tertiary datums are going to be the surfaces that we're locating from. Okay. So in this case, we are going to locate from the center plane created by the vertical dimension. Okay, so notice it would be a center plane here. And then we'd have a center plane for this horizontal dimension. So that would be coming through here. And what that does for us, notice that we don't have a center plane with a dimension to the center of the hole and then between. What that does for us is it says, okay, whatever this dimension is, we're going to do the center and we're just going to evenly distribute the location of those holes on either side. Same thing for this orientation. Okay, we're going to find whatever that width is. Okay, notice here that that's going to have plus or minus 20 thousandths on it. So whether it gets wider or not, it's going to depend on the center plane. And then from that center plane, evenly distribute that 0.75. Okay. Oh, no, I'm sorry, not 0.7. No, the 1.25, the basic dimension. You have to put basic dimensions on these locating dimensions. Have to. Because again, the tolerance is not coming from the title block for that. It's coming from our diameter of 5 thousandths at maximum material condition, then bonus tolerances and such for the sizes. Okay. Questions? Did it all come back? Don't say that out loud. No, but hopefully sounded familiar to you, right? This is the second look that you're getting at GD&T. You guys had, a lot of you had it with me in spring. Okay. So it was probably a little fuzzy at that time. Now it might still be a little bit fuzzy, but it might be a little bit more clear. All right. When we start applying it here. So, so that's my intent. That's why I want you kind of re-looking at this again. Okay. All right. So ABC, ABC. The other one that we're going to do here is going to be the 2 holes that we have vertically in this direction. These are going to be the threaded holes. Now, in this case, these threaded holes are only going to have our socket head cap screws in them. And those are just kind of in and out to kind of stabilize the rack. They are not going to be used to locate into other holes. So what we want to do for these is instead of using the fixed or the floating, because it's really neither, what we want to do is we want to use, and we want to take the dimensions that we have here and just convert them to positional tolerances. Okay. So do you guys remember doing that? Like converting existing rectangular tolerances that we already knew were okay to position. Kind of remember it? Okay. It was the circle chart thing, but we're not going to use the circle chart. We're just going to calculate it. Okay. So to calculate it, if we know, so for instance, we look at the dimensions that are here. We know that if this is a 3-place decimal locating this, we know that it's going to default to the 3-place decimal plus or minus 5 thousandths. Okay. Horizontally and vertically. Normally we would have a dimension to the center here, but in this case, because we're using the scheme that we are, it's going to be centered on the width of the part. Okay. So vertically or horizontally, we don't have one, but it would be controlled on that very same value. So that means like we have a tolerance zone. Okay, here's our nominal value. We have plus and minus 5 thousandths. I'm going to make these even. Plus and minus 5 thousandths and plus and minus 5 thousandths this way. So that creates a rectangular tolerance zone, right? With 5 thousandths on this side, 5 thousandths on that side, right? We want to know what is this distance, because that is going to be the maximum radius that we have when we're allowing 5 thousandths here and 5 thousandths here. Okay. So if we look at this, this is a right triangle and we want to know what the radius is, right? And if we double that radius, that's going to be our diameter of our tolerance zone. Okay. So if I want to find the leg of that right triangle, how do I find that? There's no. Pythagorean's theorem, exactly. So I can say that my radius is going to be equal to the square root of 0.005 squared plus 0.005 squared. What is my radius? You should all be doing it. What was that? 0.007 confirmed. Anybody else get that number? 0.007. Everybody should be doing it. You should, I can't imagine you're not curious. Oh, Lex got 0.007 as well. Okay. All right. So that's confirmed. So now that's the radius. If I want to fill in the diameter here, what do I do with that radius? I multiply it by 2. Okay, so 0.0014 is the diameter, right? Or I'm sorry, 0.014 diameter. Okay. So now when we go here, again, this was just a placeholder for us. I wanted to go through this calculation and I'll know if you were following along. 0.014 is the diameter there. That converts the rectangular tolerance zone here to a circular. So if you recall, when we looked at this back in GD&T, if this is my nominal value and we did a plus or minus 5,000, so you remember how we said, if these 4 corners work okay, right? That means that the radius going here, if that's 14 thousandths, that's more than 5 thousandths in one, or I'm sorry, 7 thousandths, that's more than 5 thousandths. So what we create is we create this arc going across or all the way around, right? And what it allows for us to do is by just taking that rectangular tolerance zone, knowing that those 4 corners work, well, then that means that all of this area is also going to work, right? And how much did we say was added to the acceptable tolerance zone? Do you guys remember the number? 57% more acceptable area. Now, that doesn't mean we're going to be getting that many more parts that are going to be good, but we've increased by 57% the acceptable area, which means we won't be rejecting good parts. We would have rejected a part up here and it would have been okay. Remember what I said? It's worse to reject good parts than it is to accept bad parts. Bad parts will catch somewhere along the line. If we reject good ones, now we just left money on the floor, right? We threw it out. That's bad. So we always want to, when we have features of size, holes, threaded features, anything, when we're locating it, we want to use position because now we optimize the tolerance zone, whether that's through bonus tolerances, but also we now are using a circular tolerance zone. We get more acceptable area, meaning that we're not going to be leaving any parts out that will fit, that otherwise we would have rejected. Okay. So this one is a converting. Okay. And this one is the fixed fastener situation. Now, I've got this whole location here, and these are going to thread into, and that's what's nice about this, is it becomes really easy. This is going to thread into these holes right here, right? So now we're going to take that very same value, okay? The very same feature control frame. This is going to be a position tolerance, and we're going to use the diameter of 5 thousandths. It's going to go right in there for our value. We're going to use the maximum material condition, okay? And then I know I'm going into my part here, but I'm a little bit larger on my size that I'm writing this out. Now I've got to add my datums, okay? So when we look here, main mating surface, this front face, this is going to be a datum, right? So we want to add a datum here. You could add flatness here, but you'll notice that you have a nice tight tolerance within 2 thousandths already. It's going to be nice and smooth. It's going to be nice and vertical. You do not have to add a flatness to that because it's automatically going to be nice and flat based on the limits of size to that value. Okay. If it wasn't and there was more variation, you would want to do a cleanup cut then and then become a datum. But in this case, the way that the dimensioning is, you're fine. So that's our main mating surface. That's going to be our datum A. So A is going to be in our first spot here. Okay, you're not going to go over the top of your part. Our secondary and our tertiary are going to come from where this is located from. Okay, so you'll notice that when we look at the dimensions here, I'm hoping this comes in clear. Our dimension is coming from the center line of that bore. Okay, it's going up. So if we look here, that means that the center line of this hole is what is going to be in the middle. That's where that 1 inch is coming from, and then 2 inches between. So our diameter, once we have that datum, or once we have it limit dimensioned, this is going to be our secondary datum. It's going to be datum B. Okay. And you're gonna put that in line with the dimension, because this is the center line that's going through here, and we want this to be up 1 inch and then the width. So locating it here, that 1 inch becomes a basic dimension, the 2 inch becomes a basic dimension. Make sense so far? Now, width-wise, we've got to look here and we've got to see, okay, where is the width or the center plane of this particular feature? Now, there's a couple places that we could get it, okay? There's a couple places that we could get it. And this kind of becomes your choice, if you would. So I'm noticing, I think I forgot a dimension. I'm noticing that I'm not seeing it on here unless I put it somewhere else, and I don't think I did offhand. I need a width dimension here for the width of that cast, the outside cast surface, okay? I'm sure it's on here. Yeah, it's 1.75. I'm not seeing it here. No, it's, oh, it is. It's right there. Thank you. I was hoping I didn't miss it. I don't know if I like it there now, but this right here, oopsie, I'm sorry, not a basic dimension. Sorry. This is going to be our datum in line with the dimension. Okay. So that's B, and this is going to be C. So in line with that dimension, this is going to be a center plane created, and then these two holes are going to be evenly distributed, and our basic dimension is the 1.25. There we go. And then we're going to put B here and C. And that's as far as the GD&T I'm going to be really worried about. I wanted you to apply some positional tolerances, this fixed and floating, we use the fixed, and then also converting the dimensions there for those features of size. You could add it in more places if you want, okay? But I just wanted to kind of line those two up and kind of ease into it a little bit for you and create a little bit of a review, not go crazy. Because I would rather you understand the couple of places here as opposed to getting overwhelmed with putting it in too many places. Does that make sense? Okay. All right. Questions about the GD&T. So where you're going to be applying it is going to be on this part here. And once we get that value, you're going to apply it right here with what we had just looked at. Okay. All right. Any questions on that portion? Okay. If not, then I'm going to stop this video and then we'll start a new one for looking at the assemblies. Okay. That way you have shorter ones, shorter ones that you can go back to when you need to.